Hello everyone, and welcome to the January Model Aquatic Health Code Network webinar titled Indoor Air Quality and Swimming Facilities with our featured speaker, Dr. Ernest Blatchley of Purdue University. My name is Grace McLean, and I'm a program analyst with NACCHO. Please use your computer speakers to listen to the presentation today, and you're encouraged to use the chat box to ask any questions you might have throughout the duration of the webinar. At the end of the presentation, our speakers will address your questions in the order that we receive them. Finally, this webinar is being recorded, and a link to the recording will be distributed to all participants. So first, just a few updates from Doug Sackett, the Executive Director of the Council for the Model Aquatic Health Code.
Thanks, Grace. Can you hear me okay? One brief update really is about the Indoor Aquatic Facility Ventilation Design and Air Quality Ad Hoc Committee, which is going to be providing some preliminary information to our key speaker today regarding this topic. The issue with indoor aquatic facility air is over the last several years, we've had poor indoor air quality has increasingly been linked to health effects. We're getting increased reporting of the health events associated with these indoor aquatic facilities. The large indoor facilities have proliferated, and these are like you're seeing more of the indoor water parks, and as such, the activity is a lot longer. The bather exposure time is longer. It's a destination. Folks will be there for hours at a time instead of going in for a quick swim and leaving. And from what we've been seeing, even from as we start developing the initial criteria in the MAC for ventilation, does not appear that the ventilation standards are adequate to keep up with the aquatics need. So hence the ad hoc committee being established by the Council for the Model Aquatic Health Code. And here's the roster for the committee. The chair is Ralph Kittler, and you can see that Chip Blatchley, Dr. Blatchley, is a member of the committee. We've got some experts from a lot of the industry, from air handling to engineers to architects and operators are part of this committee. And the basic charge for this committee was to identify and assess the factors that affect the air quality at the indoor aquatic facilities, including the air handling, air distribution system design, effectiveness, and operation. It's not just the air handling that's could be problematic. We know that water quality, water chemistry is kind of the root of the problem. So the committee is looking at that. Pool water treatment operation, maintenance, pool types. There's a big impact, whether it's flat water, agitated water, spray features, or hot water, and bather load and spectator areas. So the committee is to be looking at all those aspects to see what the impact is, and then to review and evaluate Model Aquatic Health Code requirements to determine if identified factors affecting air quality are adequately addressed. And subsequent to that, develop revisions of the MAC design and operational standards to better address the air quality. And as part of that process and part of that work by the committee, there's identified a lot of different information that's going to be needed to answer some of these questions to move forward. So hence the research proposal that was requested by the ad hoc committee, which Dr. Blatchley put together, and he's going to speak to today, is to try to answer some of these questions, bring data back so that it can move forward with appropriate design and operational updates to the MAC. And before I turn it over, one last reminder for today, too, is to renew your membership to CMAC for the 2018 to 2020 conference. Everybody's membership expired November 2017, so we're in the next cycle. I'd encourage you to go online and sign up. And Grace, I'll turn it back over to you.
Great. Thank you, Doug, for that great introduction. And next up is Dr. Ernest Blatchley. So Dr. Ernest Blatchley III is a professor in environmental engineering in the Lyell School of Civil Engineering and the Division of Environmental and Ecological Engineering at Purdue University. So thank you very much for being here today, and the floor is yours.
Okay, thank you. All right, so I'm going to be talking about indoor air quality in swimming facilities. So let me just give you briefly kind of an overview of what I plan to present. First, I'll provide just some background, why do we care about this? And in particular, why do we chlorinate pools? Because I think it's important to establish that. And then among the drawbacks of chlorination are the form of disinfection byproducts. I'll talk about those disinfection byproducts, or DBPs, that are relevant in pools and their precursors, with particular focus on the volatile disinfection byproducts. Then I'll talk about the health effects of disinfection byproduct exposure in pools. In other words, what are the effects of disinfection byproducts on people? And then I'll turn that around and talk about the effects of people on disinfection byproducts and how that relates to indoor air quality. And then I'll conclude kind of the first part of the talk with a brief presentation of some of the physics that are responsible for the transfer of disinfection byproducts from water to air. The second part of the talk will address some planned research that we hope to start within the next 10 days or so. And I'll present the scope of work and methods that we're going to be applying in that, the selection of pools, modeling work, and what we expect as the outcomes. And then conclude with some remarks on the relationships to other indoor air quality facilities. And then at the end, we'll have some Q&A. Let me just kind of dive in. So I think I'm probably preaching to the choir here. We know why it is that people choose to use pools for exercise, recreation, and therapy. Swimming is the second most common form of exercise in the United States and has a number of clear benefits in terms of improved cardiovascular health and fitness. It's also used as therapy for a wide range of medical conditions. So there's lots of different reasons why we have these facilities. Among pools, again, still preaching to the choir, there's a requirement in most applications for treatment of the water. That treatment is going to involve generally two groups of processes. The first are physical separation processes for removing particles. Those will involve a filter or membranes or both. And then the second group of processes I've just lumped together as disinfection and oxidation. Chlorine is by far the most common agent that's used to promote both disinfection and oxidation. But there certainly are alternatives that are relevant. They include, among other things, UV, ozone, and monopersulfate, and there are some combinations of these things that are added as well. So these things all will play roles in both water quality and air quality, but my focus today is going to be on the chlorine side of things. So in terms of, why do we chlorinate pools? It's mostly to address those issues that I just described, and the reason that we've chosen chlorine for most of these applications is, number one, it's very effective as a disinfectant against bacteria and viruses. Chlorine is also a powerful oxidant, so that allows us to not only disinfect water, but also to degrade by oxidation constituents that are left behind in the water, usually by swimmers. Chlorine is also really inexpensive in a relative sense and pretty simple to use. There's a long history of its use, and so people are pretty comfortable with it. But it's important to point out that there are disadvantages of chlorination as well. So those include that it's very ineffective against Cryptosporidium. That's this organism down here. And also, when we consider disinfection and the specific microorganism Cryptosporidium parvum, there are data that exist in the literature. For example, this data that were published by Michelle Hlapsa and her co-workers at CDC that indicate that Cryptosporidium is the dominant etiologic agent that's responsible for recreational water illnesses of microbial origin. So, and that's really largely attributable to the fact that first, crypto ends up in water, and second, chlorine is almost useless for inactivation of it. The second major disadvantage of chlorination is the formation of disinfection byproducts, or DBPs, and that's going to be the focus of what I'm going to be addressing here today. So there's a number of disinfection byproducts that exist in pools. There's more than 100 that have been identified in swimming pools. They include volatile and non-volatile forms. Because I'm going to be focusing on air quality, I'm going to focus intentionally on the volatile disinfection byproducts. There's several groups of these compounds, and we find them in almost every pool. So the first one is the group that probably most people are familiar with, and that is the group that we call the inorganic chloramines that include monochloramine, dichloramine, and trichloramine. Trichloramine is important because it's largely responsible for the odor that we detect in association with indoor swimming pools. And it is easily the most volatile of the inorganic chloramine compounds. Among organic chloramines, there's one that we find regularly in swimming pools, and that's called dichloromethylamine. That's this compound right here, CH3NCl2. Then there's a group of trihalomethanes, or THMs, that are substituted either by chlorine or bromine or both, and they show up regularly in pools. And then lastly is this group that we call the halogenated nitriles. They include this compound, which is cyanogen chloride, this compound, which is cyanogen bromide, and this compound, which is dichloroacetonitrile. So those three compounds are relevant because they're volatile to varying degrees and they're toxic. Again, just to reemphasize, these compounds are present in basically every swimming pool. In other words, pretty much any time you put swimmers and chlorine together, you're going to get these compounds. So the data that I'm presenting over here in this graph on the right illustrate measured concentrations of mono, di, and trichloramine that we conducted about 10 years ago in a group of 11 pools that are fairly close to my lab, where we can get water samples fairly easily. And for each of these things, they represent, 30 or 40 measurements that we did at these pools over a period of about 6 months. And so what we observe is that within each of these pools, there's considerable variation in the concentrations of each of these things. And across the pools, there's also variation that shows up. But in a general sense, we find all of these compounds in pretty much every water sample that we collect from a chlorinated swimming pool. And they're all volatile, which means they all have the potential to end up in the gas phase. All right, so then a question, where do these things come from? Most people consider the chloramines to come from chlorination of ammonia. And that is kind of the conventional way that they are formed, and that's really what kind of informs most of our understanding of these chemicals. But in swimming pools, there's almost no ammonia that's present. So what that means is that these compounds really come from organic nitrogen compounds that contain reduced nitrogen. And that organic nitrogen is introduced largely in the form of urine and sweat, and it includes these compounds that are listed over here: urea, creatinine, uric acid, and amino acids. So these are, products of metabolism that show up in human urine. They also show up in human sweat, and because of that, they end up in swimming pools. So when we look further at, how much of these various body fluids end up in swimming pools, it might surprise you. So there have been several studies that have been conducted to identify how much, for example, urine ends up in a swimming pool. So I've quoted two studies here that indicate somewhere between 30 and 80 milliliters. I've seen other work that suggests up to about 100 milliliters. And just to put this in sort of practical terms, that means that pretty much if you look at a pool and you count the number of people in it, you can multiply that number of people times roughly the volume of a shot glass, and that's how much urine they have contributed to the pool. And that's pretty much what you can expect. When people are in a pool, if they're exercising hard, they will also sweat. Competitive swimmers will release up to 1 liter per person per hour of sweat, and that's why hydration has become such an important part of the training regimen of competitive swimmers. And then lastly, there is this group of chemicals that are called natural moisturizing factor that's important in the skin for retaining moisture. They include urea and amino acids and some other compounds, and these compounds are all very hydrophilic, which means they're very soluble in water. So that's really sort of explains why your skin becomes wrinkled after you've been in the water for a while. This natural moisturizing factor has been removed from your skin, and your skin will start to dry out, despite the fact that you just come from a swimming pool. But those chemicals, when they're released to a pool, also can participate in these reactions that I described before. All right, just quickly, I want to point out that there has been a fair amount of work, actually, to evaluate the health effects of chemical exposure in chlorinated pools. And I'm going to focus on health effects that are associated with volatile chemicals, in other words, the chemicals that end up in the gas phase. So just to highlight, this study, which was conducted by a group in Belgium that's headed up by Alfred Bernard, pointed out that attendance at chlorinated swimming pools exerts unpleasant effects on the respiratory system that may show up in terms of asthma or hay fever or allergic rhinitis during adolescence. A second study by the same group came up with a similar conclusion relating to infants that are exposed to chlorinated indoor swimming pools. They did some other groups have published work to come up with more or less similar conclusions regarding not only swimmers, but also the employees at a swimming pool. So it's pretty much people who are exposed to the air environment in an indoor swimming pool that are exposed to these chemicals. They are subjected to stress on their respiratory system. This is one other study in which a summary was done of a particular event that took place in Ohio, where there were chloramines that were released from the liquid phase to the gas phase. And if you look at the list of symptoms that are over here, most, but not all of these symptoms relate to the respiratory system. So in a more general sense, we can sort of summarize the health effects that are associated with chemical exposure in chlorinated pools, especially indoor pools. And at the top of the list are respiratory problems, in other words, stress on the respiratory system. So there's more than 100 articles that have been published in the last 40 years or so that address this issue, and it's pretty clear that there is a link. There was a study that I'm aware of that was published a little more than a decade ago that was, the primary author was Krista Villanueva from Spain, who demonstrated that there was a link between increased incidence of bladder cancer and time spent in a chlorinated swimming pool. And then lastly on this list anyway is eye irritation, which I think we're all familiar with if we've spent any time in a swimming pool at all without goggles on. All right, so those previous slides were talking about what is the effect of disinfection byproducts on human health. Now what I want to do is to consider the opposite. What effect do swimmers have on disinfection byproducts, especially those compounds that end up in the gas phase? So this is data that we collected during a study we conducted about 10 years ago, in which we were measuring trichloramine in the gas phase in an indoor swimming pool. So on the vertical axis here, I've represented the concentration of gas phase trichloramine. On the horizontal axis is time, basically. And what we see, the dots represent the trichloramine concentration, and we see that that concentration varies throughout the day and across this period that we were sampling. For reference, I put these two lines, the green line, which is a guideline value that Alfred Bernard's group suggested of 0.3 milligrams per cubic meter for trichloramine, and the World Health Organization has established a different guideline of 0.5 milligrams per liter. So I just put those up there for reference, and basically what this suggests is that when the concentration exceeds one or both of these limits, that's when we start to expect to observe respiratory stress. People start coughing, their throat gets sore, that sort of thing. So in looking at these data, there's a trend that shows up pretty clearly, and that is that the highest concentrations here are associated with periods where the pool was being used heavily. So the blue bars represent the bather loading in the pool, and we see that the periods of time when the pool was being used most heavily, again, are the periods of time where the trichloramine concentration was the highest. So here's a second data set that illustrates more or less the same trend. Again, the concentration of trichloramine starts to go up pretty rapidly when the pool becomes crowded. And we've seen that in many pools. This is a much more dense data set that was part of a study that we just completed late last year, 2018. And there's 4 measures of indoor air quality that we measured with a device that I'm just going to describe as an IAQ monitor. So that IAQ monitor allowed us to collect measurements in real time of trichloramine, that's this panel, carbon dioxide, that's this panel, relative humidity or water vapor, that's this panel, and volatile organic compounds, that's this panel over here. If we look first at the trichloramine panel, here are those same 2 reference lines from Bernard and from the World Health Organization. And superimposed on this, although it's difficult to tell, at least on my screen, the sort of darker bars are the bather load. And what shows up again here is that there's pretty good agreement between the periods of time when the bather load was high and the periods of time when the trichloramine concentration was high. Now, I haven't put the bather load on either of the other 3 panels over here. You'll just have to take my word for it on here. There's good agreement also that exists between the concentrations of these other constituents and the bather load. In other words, when we have a lot of swimmers in a pool, we can expect that volatile chemicals that are present in the water are going to be promoted. Their release is going to be promoted from the liquid phase to the gas phase. And so obviously that's going to have profound effects on air quality in these indoor swimming pool facilities. All right, so I want to talk just for a minute about the physics that are responsible for transfer of chemicals from the liquid phase to the gas phase. And I'll use the so-called two-film model to illustrate this. The two-film model is probably the fundamental model that's used to describe transfer of chemicals from the gas to the liquid phase or in the opposite direction. And one of the central hypotheses of this model is that we can simulate the transfer of a molecule, let's say from here in the bulk liquid phase to here in the bulk gas phase as a series of steps. So the first step will be to go from, let's say, here up to this green dashed line, which is supposed to represent the edge of a hypothetical liquid film that exists right next to the gas-liquid interface. The idea with this film is that we assume that transport across that film is going to be limited by diffusion and therefore will be relatively slow. So the molecule will move from this location to this location relatively quickly, but from here to here, we expect that it will move very slowly. Similarly, on the other side of that interface, there's going to be another film in the gas phase, and we expect that transport will be by diffusion there and also will be relatively slow. And once the molecule makes it to the edge of this gas film, then it'll be transferred into the bulk gas phase relatively quickly by mixing behavior. So the kind of curved arrows that I've shown over here are being used to sort of illustrate in sort of qualitative terms the mixing intensity that exists in both the liquid and the gas phase. In this example, the liquid is not being mixed very aggressively, and the gas is being mixed, well, maybe a little bit more aggressively. So the basic idea in this is that because transport across this film, the liquid film, and the gas film are relatively slow, we expect that one or both of them are going to be the rate-limiting step that will govern how fast this chemical moves from the liquid phase to the gas phase. So we describe that mathematically based on this equation. The left side is a so-called mass transfer coefficient, or the inverse of a mass transfer coefficient, that represents the resistance that's offered by this entire system. The right side includes two terms. The term all the way over on the right, that's this term right here, represents the so-called liquid film resistance. That's the resistance that the molecule experiences in going across that part of the system. And then the next term over here, this one describes the gas film resistance. That's the resistance that exists over here. So if we take a chemical where the majority of the resistance is offered by the liquid film, then one way to promote its transfer, or in other words, increase the rate of its transfer, is to mix the liquid more aggressively. So if I go to the next slide, what's going to happen is we're going to mix more aggressively, and the liquid film will become thinner. As a result of that, the time for diffusion will decrease, and the overall rate of transport will then increase. And so that's kind of the basis of this model. And the chemicals that we're most interested in are chemicals that are dominated by liquid film resistance. So let me just kind of demonstrate that using a couple slides. So this is a collection of data that describe, first of all, typical concentrations of compounds that we see regularly in swimming pools. And then the next column represents the Henry's law constants for each of these compounds. So if you're not familiar with Henry's law, it basically describes how volatile a chemical is. So the larger the value of a Henry's law constant, the more volatile a chemical is. So you can see that trichloramine is pretty volatile. The next column represents what we would calculate to be present in the gas phase if the gas phase, in other words, the air above a pool, was allowed to come into equilibrium with the water that was in the pool. And then the last column represents concentrations that we actually measure. So I'm going to zoom in on just trichloramine to point out that when we look at the actual concentration that we have measured in swimming pools, it's about 1% of the equilibrium condition. And that's really important because if we ever got to an equilibrium condition in a swimming pool, everyone in that pool would be suffering. And it would be a really uncomfortable situation at the very least. And the reason that we never get close to these equilibrium values is that we operate HVAC systems that bring in clean air from the outside, rinse away most of these chemicals, and flush them to the outside. And we really depend on those systems. If they stop behaving, then we'll go from this condition and start approaching this condition, which is clearly undesirable. Okay, so just to kind of reiterate, some of the text on this vertical axis is not showing up on my screen, but it basically represents the fraction of resistance that's offered in each phase. And what's perhaps important is this blue line, and that represents a condition where the resistance in the liquid film and the gas film are equal. And so pretty much every chemical that lies to the right of that dashed green line is sufficiently volatile, in other words, has a large enough Henry's constant that its transfer is dominated by resistance in the liquid film. So what that means is that if I promote conditions in a pool or if I establish conditions in a pool that allow for the transfer of that chemical, trichloramine, we can expect that those same conditions will allow for transfer of all these other chemicals to a similar degree. We'll still get transfer of these compounds, but they're a lot less volatile, and their ability to escape is also going to be much smaller. Okay, now I've highlighted radon down here in the lower right, largely because I'm going to go on a bit of a tangent here in just a minute to talk about radon and how it might play a role in swimming pools, but at the very least, what we know about the behavior of radon in indoor swimming pools, or in indoor environments, I should say, does teach us something about how we should treat indoor swimming pools. All right, so in a general sense, I just want to summarize the factors that affect air quality in indoor swimming pools. Clearly, water chemistry is going to play a role. Mixing of the liquid phase is going to play a role, and we see that that shows up in the form of, for example, swimmers, but also spray features that exist at parks. Mixing in the gas phase, in terms of the operation of the HVAC system, is going to play a role. Water treatment, largely because it's going to affect water chemistry, will also play a role. And in a general sense, at least qualitatively, we understand that. But what is lacking is a quantitative understanding, and that really is what has motivated this study that we're about to start. So what I want to do is to talk about what it is that we're going to do in this study and what we're hoping to accomplish in this work. So first, what we want to do are to define the relationships among various design and operational parameters of swimming pools and indoor air quality. In other words, how is a pool designed and operated, and what does that imply in terms of indoor air quality? We will focus on trichloramine as what I've identified here as a sentinel compound, but because of what we know about the physics and also measurements of the behavior of other volatile chemicals, there are other chemicals that might represent reasonable proxies for trichloramine, and we're interested in them not only because they might be a good proxy, but also some of them are a lot easier and less expensive to measure than trichloramine. Secondly, we want to be able to quantitatively define mass transfer of these volatile compounds and how that associates with various mixing regimes that exist in pools. So those regimes include baseline conditions when the pool is not being operated or is not being used by swimmers. Second of all, transfer that's associated with swimmers. And lastly, transfer that's associated with various water features. And lastly, then, we want to use that quantitative information to develop recommendations for facility design and operation so as to improve indoor air quality. All right, so let me just describe the project itself. The project will take place in two phases. Phase one, we hope to start within the next week and a half. This is going to be conducted as a collaboration with some colleagues of ours at Michigan State University from the College of Medicine. My group at Purdue is going to be conducting measurements of water chemistry, air chemistry, and also characterizing the pool in terms of how they treat their water, how their HVAC system has been designed and operated, and what is the bather load. The group from Michigan State is going to be conducting some physiological measurements in parallel, simultaneously with the measurements that we conduct on the pools themselves. So this first phase of the study is going to be conducted at competition pools and we're going to focus on those pools over the next 6 months when they're scheduled to have relatively large swimming competitions, meaning that the bather load in these pools will be relatively high. So we'll go into these pools before the competition starts and continue our monitoring through the competition so that we can characterize the effects of the heavy bather load, which we expect to be the worst conditions that these systems are likely to experience. Phase 2 will then continue with a particular focus on the chemistry side of things. We'll also continue to characterize the pools as we did in Phase 1, but in Phase 2 we're going to expand the range of pool types to include things like therapy pools and splash parks. So we're not going to focus exclusively on competition pools, and we're going to be looking at a broader geographic distribution than the distribution that will show up for Phase 1. In Phase 2, there will be a two-stage survey that's going to be used to select these pools, and the idea is to get a population of about 15 pools to include in Phase 2 that allow us to say the broadest, most important things about indoor air quality and these other factors that I've described before and how they relate to indoor air quality. Okay, there's a series of measurements that we're going to conduct. In terms of water quality, we're going to be measuring urea. There is a relatively simple method that allows us to do this by digestion, followed by a colorimetric assay. We'll measure total organic carbon, pH, using conventional instruments. We'll use conventional colorimetric measurements to measure residual chlorine. We'll measure temperature just because it's easy to measure and it's also important. And then lastly, we'll measure volatile disinfection byproducts using a method called MIMS that I'll describe in just a minute. On the air side of things, we're going to be measuring indoor air quality with this IAQ monitoring device. It allows us to measure in real time, simultaneously, all 4 of these parameters: trichloramine, relative humidity, carbon dioxide, and VOCs. So we're going to, in parallel with that, we'll do some selected measurements with a wet chemistry method for measuring trichloramine, and we'll also measure other characteristics like relative humidity, CO2 and VOCs using other relatively inexpensive off-the-shelf instruments for measuring this. For reasons that I'll describe in a minute, we may have an opportunity to measure radon as well, and then lastly, we're going to use corrosion coupons to measure corrosion responses during this same period. All right, so just briefly, I want to describe this wet chemistry method that we use for measuring trichloramine in air. We're going to use an air pump to draw air into a series of gas washing bottles, 2 in series. And in those gas washing bottles, we're going to put an aqueous solution of DPD and potassium iodide. The idea is that combination of DPD and potassium iodide will react very aggressively with trichloramine that's in the air, and it'll trap it in this solution. And then the solution over here will turn pink in response to that. So then we can measure how much pink has shown up, and we can translate that into a trichloramine measurement. So here's an image of that assay that's being used, and you can see this kind of faint pink color that's showing up in the first of these 2 tubes. Air is going in here, and it goes out, goes in here, and it goes out through this pump, and then out. Okay, and that's a method that we've used in the past to measure trichloramine. Another method that we're going to use is called membrane introduction mass spectrometry, or MIMS, and this is a method where we take a sample of water and we introduce it by a pump into this little tube here. That water sample is then going to encounter this device that we call a pervaporation membrane. It's just a small diameter tube that has a material that allows volatile chemicals to diffuse through the wall of this membrane, and non-volatile chemicals will not. So what we've found is that we can use this method to measure volatile disinfection byproducts in water. And what happens is after they go through this membrane, they get on the other side of the membrane, and then they're in the gas phase, and they're swept in the opposite direction by an inert gas into a mass spectrometer where they can be measured and identified. So this method is very powerful. It's also really simple and quick to conduct, and we have one of these instruments in my lab. So the pool characterization will include a number of things like, for example, bather load that we can quantify just with a digital camera, the characteristics of the air handling system, the characteristics of the water management system, and general maintenance practices that are used at each of these pools where we're going to be collecting data. Okay, so I mentioned a minute ago that I want to go on a bit of a tangent, and this is just sort of a coincidental situation that has shown up. So last week I was contacted by Jessica Maloney from the Wisconsin Department of Health Services in Madison, Wisconsin, and she described for me a situation that she had encountered where in some of the fisheries that, the fish hatcheries that exist in Wisconsin, which are indoor facilities for obvious reasons, the radon concentration in those facilities can be quite high. So she sent also some images that she allowed me to use in this presentation to describe why that is. So these PVC columns that show up here along the wall, these are being used to oxygenate the water that's being brought into this system. So this particular hatchery uses groundwater, and that groundwater is relatively low in dissolved oxygen. So they want their fish to be happy, so they're going to transfer oxygen into that water before they send that water into these tanks. One of the problems with using these basically aeration columns is that they allow for transfer of oxygen into the water. They also allow for transfer of volatile chemicals like radon out of the water. So what's happening is they're pumping about 2 million gallons of water per day into this facility, and they're stripping the radon right out of here, and it ends up in their indoor air. And that's caused a problem for them. So their stripping towers, that's these things right here, are packed like most stripping towers are with this kind of plastic packing to promote transfer. So again, that's very effective in promoting transfer of oxygen. Unfortunately, it's also promoting transfer of radon. So they implemented a relatively crude system for improving the air quality in their fish hatchery system, largely for the protection of their workers. So they did this really just by opening doors and windows and installing fans. And as a result of that relatively simple approach, they went from this condition over here where they were getting radon concentrations as high as 200 picocuries per liter or more, down to this level, which is, considerably lower, just by opening windows and doing that sort of thing. So that was a step in the right direction, but for them, it's nowhere near good enough. And just for reference, this red line that I'm pointing to right now is the so-called action level for radon. It's 4 picocuries per liter. So they're still way over that in this configuration. So what they decided to do was to move their air stripping outdoors. So they're adding oxygen here to the water that they're bringing into the system, and at the same time, they're now stripping the radon out of the water, and then that aerated water is then being sent into the building to use as it had been before. And when they did this, they basically solved their problem. Now they have a radon concentration which is basically hovering right around this action level of 4 picocuries per liter, and they're okay with where they are right now. But the point is they went from 200 picocuries per liter to 4 as a result of this. I don't know if radon is going to be a problem in indoor swimming pools because they don't use anywhere near as much water as a fish hatchery will. But on the other hand, there are no data that I'm aware of that describe radon concentration in indoor swimming pools. And so thankfully, Jessica has volunteered to allow us to use one of their radon meters for purposes of measuring radon concentration, and we plan to implement that as part of this study that we're about to start. Okay, so just to sort of wrap up, where we're going with this work is that we want to collect these data about mass emission rates of these various compounds and also indoor air quality. And we want to incorporate that into a model to describe the behavior of this system. So the model itself will include terms to account for mass emission that's attributable to just ambient circulation, swimmers and the various water features that exist at this system, and the other characteristics of the system. And what we want to do is to see how does this model and its predictions compare with the actual measurements that we have from these facilities where we're going to be collecting this information. If we are then able to successfully demonstrate that the model has been both calibrated and verified using these data, then the plan is to use the model to ask some what-if questions and to inform what we would suggest about how these facilities should be operated in the future and designed. So what I expect to come from this is, first of all, quantitative information about the relationships of indoor air quality to things like pool design, pool use, water treatment, and the design and operation of the HVAC system. In turn, we will then use this to provide recommendations for how pools should be designed and operated. And along the way, we want input from the swimming community because they're the people who are going to be most affected by this research. So I'll just, with that, say thank you and then attempt to try to answer some of the questions that have been asked.
Great. Thank you so much, Dr. Blatchley. We have a lot of good questions from the audience, so I'm going to go ahead and start with the first ones that we received.
Okay.
So we had someone ask at the beginning, they had to leave, but we asked if you'll be using AOP technology included with UV and ozone for evaluations.
So in phase 2 of the study, again, the idea is to consider a broad range of pools in terms of the various attributes that we think will affect air quality. And the pools that are going to be included in phase 2 will be identified by this two-step survey. So really, for any pool to be included, they need to, the people who own, operate, manage, whatever, the pool need to participate in that survey. So my understanding is that survey is going to be sent out to the swimming public across the country to try to encourage as many people as possible to participate. We're using 2 stages in this survey. First stage is really just to try to identify facilities that may have an interest, and then second stage is really going to be to focus on the facilities from the first stage that look most promising in terms of trying to meet the goals of providing the broadest spectrum as possible. So, I mean, to answer the question specifically, we haven't zeroed in on any particular technology, and we want, all aspects of the pools to be as broadly represented as possible.
Chip, this is Doug. Can you hear me?
Yes, I can.
Just to add to that too, on the CMAQ website, there's on the home page you can click to fill out the CMAQ air quality survey. So we have the first part of that up and available right now to access and get signed up.
Great, thank you, Doug.
Awesome, thanks for addressing that. We have a question about if the pool that you looked at, the first one you mentioned, had, I think, a medium pressure UV is the question.
Boy, I'm not sure which pool you're referring to, but honestly, I'm not sure if any of these pools, well, that one clearly doesn't, but I'm not sure if any of these pools had medium pressure UV in them.
Okay.
Yeah, I mean, perhaps there would be a follow-up question to try to address that. I mean, so medium pressure UV is very commonly used in pools, probably more commonly than low pressure UV. And some other work that I didn't present here that we've conducted in the past suggests that it might be favorable to low pressure UV in a sort of holistic sense. UV is used for 2 reasons in swimming pools, at least that I'm aware of. One is for inactivation of cryptosporidium. It is the best disinfectant for inactivation of crypto. And second, UV is effective for breaking down chloramines. So anyway, if there's another question about medium pressure UV, I'd be happy to try to answer it.
Okay. They didn't go into any more detail, but we can absolutely follow up offline.
Okay. Okay.
So the next question was, how long of an exposure and or how frequent is related to an increased risk of the health effects?
Yeah, so I mean, in a general sense, health effects are associated with time and concentration. I mean, more or less the same way that we think about disinfection. It is essentially the same thing. I can't answer that question in a quantitative sense other than, the longer you're exposed, the worse off you're going to be. The higher the concentration, the worse off you're going to be. But that's really, to a large degree, why we have brought in these collaborators from the College of Medicine at Michigan State University. So these are people who focus on that issue specifically, and they have the expertise to address it. The expertise that we have really is much more focused on the chemistry side of things, and really what we're planning to do in this study by collaborating with these people from Michigan State is to be able to directly link the chemistry and the toxicology, the human health effects. So I'm sorry, I can't provide a direct answer to that question because it's kind of outside of my expertise, but we expect to be able to answer that question in this research.
Great, thank you. We have a question from Benjamin asking, at what level or height does the chloramine typically reside? And then a comment along with that saying that it's heavier than air, so it would probably depend on volume and mixing of the pool air. Does that sound right to you?
Yeah, this is sort of a tricky issue. So, I mean, it's true that trichloramine is heavier than air, but, you know, if you can't really translate that logic literally, because if that were true, for example, oxygen is heavier than nitrogen. And if the molecular weight of the compound of interest was the only thing that determined where it showed up in the atmosphere, then our atmosphere at sea level, or you know, where we exist right now, would be much richer in oxygen than it is. So it is true, two things are relevant in terms of kind of the vertical distribution of trichloramine in pools. Number one, that trichloramine is going to be released almost exclusively from the water. So being transferred from the water to the gas phase is what we'd expect. It is more dense than air, and so we expect that there will be some bias for it to remain close to that interface. But, you know, trichloramine is a pretty small molecule, and if you start mixing that air, it's going to be swept away into other parts of the system. I would expect in most systems that the trichloramine concentration will be higher close to the air-water interface, but I would also expect the trichloramine to be found pretty much everywhere within the airspace of an indoor pool, perhaps at lower concentrations as we move further away from that gas-liquid interface. But I think it's a little bit too simplistic to just say because trichloramine is heavier than air that it just is going to sit right there. That's not quite true.
Okay, great. We have a question from Lisa asking if the HVAC characteristics you're looking at are the ones that are reported or actually measured?
Both. So great question. So the characterization work is going to include things like, you know, the design drawings that were and the as-built drawings of the HVAC systems, but also photos of how the system was actually implemented, and then also measurements of how the system is actually being used. So there will be airflow measurements of that are going to be used to characterize these HVAC systems. And those are going to be done by people who, they're not going to be done by me, they're going to be done by people who know what they're doing in that arena.
Okay, fantastic. A question from Ron asking, will the study use pools only using chlorine as a disinfectant in order to have a solid base?
Yeah, so this is similar to the question I think that was asked about AOPs. So again, the basic idea is that in phase 2 of the study, we're going to be soliciting pools that span a broad spectrum of use types. So we're going to be looking at, you know, certainly chlorinated pools are going to play an important role, but we would expect also that pools that have different methods of treatment would also be included.
Great, fantastic. And then we have just a couple comments from people. I'm going to skip them for now in the interest of time. Next question. Will your project include testing carbon monoxide levels as a part of indoor air quality considerations?
No, that's an interesting question. We're not set up to do carbon monoxide, and I'm not. I don't see a reason why carbon monoxide would be why we would expect it to be a relevant contributor. I certainly hope not. I think the easy answer is no. It's kind of outside of the scope of what we have in mind.
Okay. Next question is, will the project address lower air exchange rates recommended by energy experts and building codes?
Great question. So again, I'm going to refer to phase 2. So I should maybe describe how phase 2 will be implemented. So earlier in the presentation, Doug Sackett listed the members of the ad hoc committee that are evaluating this. And the way that I'm expecting this to play out is that we will receive considerable input from the other members of the committee as to how we select pools from among, the various people that respond to this 2-stage survey. Among the things that we're going to be considering are, how are the HVAC systems operated, and that will be information that will be included in the survey. So I guess the answer to your question is yes. I would expect that we would see a range of HVAC system characteristics. Whether those are attributable to energy savings or something else is sort of secondary. But yeah, I would expect that we would see a pretty broad range.
Okay, great. Our next question is, how does shocking a pool affect the concentration of DBPs in the air?
Great question. So shocking is sort of a technology that's borrowed from a process known as breakpoint chlorination. If ammonia was the source of reduced nitrogen in a swimming pool, shocking a pool might make sense. But at least my opinion is that shocking a pool is going to be counterproductive, at least in the near term. And the reason is that the dominant form of organic nitrogen that exists in swimming pools is urea. Urea reacts pretty slowly with chlorine, and even under shock conditions, it reacts quite slowly. But the primary product of chlorination of urea is trichloramine. So my expectation is that you could actually see air quality get worse, at least in the short term, as a result of shocking a pool. And I would worry about air quality immediately following or during that shock event. I'm not an advocate for shocking, I guess is the way to translate that.
Okay, great. Thanks for that input and analysis. We have a question from Eric asking, will you be studying the effectiveness of fans to disperse the chloramine layer from the surface of the pool?
Yeah, so this addresses kind of two issues that have been brought up before. So, I think there is this concept of a chloramine layer because of the, attributes of chloramines, especially trichloramine that we talked about before, and that, it is released from the water. So I do expect that the concentration will be higher closest to a pool, and that's why a lot of people blow air across the surface of a pool with fans. And if they can then release that air to the outside, I would expect that to improve things. We will include that to the extent that we can include facilities like that in phase 2 of the study. Again, just kind of considering, what we're trying to accomplish in phase 2. That is not a specific objective of what we've set out to do, but if that happens to show up among the pools that are included in phase 2, then great. We'll have some data to address that.
Fantastic. We have a question about a site that folks can visit to make sure that they're on the email list to get on the survey for the test. I think Doug addressed that.
Yeah.
And we can send out that information as well in our follow-up email.
That'd be great. Thank you.
Everyone has that. Yeah, absolutely. There's a question from Carly. Will peak chlorine demand be monitored as bather load increases?
So we're not going to measure chlorine demand explicitly in this research, but we will be monitoring how much chlorine is used. So I mentioned, or I'm trying to make the distinction because there is a chemical test that allows you to measure chlorine demand, and we just don't simply have time to do that. But we will be keeping track of how much chlorine is used by the pool to the extent that we can, and that would be as close as we're going to get, I think, to what you're asking. Just as an aside, we certainly expect, based on experience, and probably have similar experience, that the chlorine usage will increase during these periods of heavy bather load.
Okay, moving right along. Will the study have a variety of pool and air temperatures to find an optimal temperature?
Yeah, I think that's again sort of referring to the phase 2. So, I mean, all of these comments about, the various things that could be incorporated into the study, these are all things that we as a committee will be considering when we select from the kind of group of respondents to this survey, what pools to include. So in a general sense, when we consider, well, both phase 1 and phase 2, we want that population of pools to be as broadly representative as possible. So there's, I'd say it's a virtual certainty there are going to be some circumstances that will not be included in this group of pools that are involved in phases 1 and 2. That's just the way it goes when we're constrained by the number of pools we can evaluate. But the basic idea is to be as broadly representative as possible.
Okay. So related to that, folks are very curious what exactly you'll include in the study, but we have a couple of people who are interested in whether one of your objectives is to provide recommendations for improvements to the HVAC systems.
That is the primary objective, really. I mean, it relates, so air quality is influenced by a whole bunch of things, one of which is HVAC system design and operation. So, I mean, that is a primary objective of this work, is to address that specific issue, yes.
Fantastic. Okay. Let's see. Apologies, I lost my thread here.
No problem.
Okay. A question about, will the project address potential radon generation in indoor aquatics? I think you mentioned this a bit in your talk.
Yeah, so again, we've been offered the use of a radon monitor, and assuming that instrument shows up, our plan is to install this in facilities and just see what we get. It could be nothing interesting, but again, we're very fortunate to have this instrument be made available to us at no cost to the project. And, at the very least, I'm curious to see what's going to happen. I would expect that if radon is going to show up as an issue in indoor air quality in these pools, it's only going to be in pools where they're feeding water into the pool that has a fair amount of radon in it.
Okay. We had another question, maybe again for that phase 2 part, about including sensory deprivation tanks, whether that's something you'll look at.
I don't think so. So I'm not a big fan of sensory deprivation in any form, but no, I don't think that's part of the plan there. But that's really more the group from Michigan State, kind of the scope of work that they're going to be incorporating into their work and the physiological measurements. They're going to be looking primarily at lung function, and I believe they're going to be doing some measurements of some respiratory proteins that are relevant, there is some information to suggest that those proteins are altered as a result of exposure to things like trichloramine.
Okay, sounds great. We have, I think, maybe our last question, and it's a good one to wrap up on. When will this study start? And will they receive any updates after each phase, or when the whole project is complete? How will that work?
So the study, our plan is to start the study February 1st, actually even before February 1st. There is, in phase 1, the plan is to be going to these competition pools before and during these competitions where there's a large number of swimmers. So it happens that there is one of the pools that we're going to be working with that has a large age group swim meet that's scheduled for the first weekend in February. So we are hoping to have our instrumentation set up at that pool several days before that competition starts so that we can get the background data and then collect data right through that competition so that we can see how it goes. First phase will, again, essentially start February 1st. It will last 6 months. Phase 2 will then start at the end of phase 1. There is at the end of phase 1, the plan is to have a review by the members of the committee and kind of a detailed review of, what have we observed, what might we do differently, that sort of thing. And then if there's approval to go on to phase 2, then we will continue in phase 2 as described by the slides up on the screen right now.
All right, fantastic. Thank you so much, Dr. Blatchley, for presenting your work on this really important topic. We are out of time for today. Thank you, everyone, for participating. And if you'd like to receive more information about our next webinar, please make sure that you're registered for the MAC network by sending your name and affiliation to macnet@nacho.org. That's MAHCNET@NACCHO.org. So thank you all for joining us, and enjoy the rest of your day.
The chairperson has disconnected. The conference will now end.